Welcome back. What we're going to do in this video is talk a little bit about the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is useful in two main areas. Well, first of all, it's useful in calculating pHs of buffers, assuming you know the concentrations of each species in the buffer. But it's also, if you know the pH of the buffer, which is something you can certainly measure, you can actually calculate the concentrations of the known species, so it can actually go both ways. And I think what you'll find is that the problems that you get in the context of your biochemistry course are actually pretty straightforward. Now, what I want to be perfectly clear about is there's two types of problems that you can have. The first type, which is actually the more difficult of the two types, is where you have a known pH, a known pKa, and a known concentration of the total buffer. Okay, this is the hard kind of equation because what it's going to involve is a system of two equations and two unknowns, so that makes it a little more difficult. The other type of problem that you're going to have is where you have known concentrations of all your species and the pKa. In that case, you're actually just going to plug in numbers straight away, so you don't even have to, rearrange the equation in any way, or take anti-logarithms and things like that. So it's actually pretty straightforward. And actually, in the next video, we're actually going to do a problem. Excuse me, that was Facebook. Anyways, we're actually going to do a problem like that in the next video, and you'll find that it's a very, very straightforward, easy type of problem. Okay, but what I want to do in this video is, now that we understand a little bit about titration curves and what's happening with them, I want to think about what might happen when you have the pH equal to the pKa. And we've already sort of mentioned it in previous videos, but I want to do a little a proof that at the pH, when the pKa is equal to the pH, that we have equal concentrations of the conjugate base and the conjugate acid. So in the context of this problem, here's the conjugate acid, and this is just a generic equilibrium right here, where HA is going to dissociate into a proton and A minus. And so on the left side of this vertical line right here, where we have 0.5 molar equivalents and the pH is equal to the pKa, on the left side of that line, the predominant species is HA, the conjugate acid. But as we move along the pH curve and we get to the right side of that line, okay, the predominant species then becomes A minus, okay? But at 0.5 molar equivalents, when the pH is equal to the pKa, we have equal concentration of conjugate acid and conjugate base. And all I want to do in this video is sort of do a proof of that. And really, there's sort of two ways to go about doing it. Let's look at the first way. And in the first way, what we're going to do is let's actually figure out what the pH is when the concentrations of the conjugate base and acid are equal. Okay, so let's think about this. Okay, so the concentrations of the conjugate acid, okay, is equal to the concentration of the conjugate base. I think I said that in reverse, but anyways, you get the point. Okay, so these concentrations are equal, right? So what we want to do in this part of the video is we want to sort of figure out what the pH is at that point. Well, notice that I can rewrite this equation then. I can say that the pH is equal to the pKa plus the log base 10. Well, if the concentrations of A minus and HA are equal, I can make a substitution, right? Let's replace HA with A minus. So that becomes the log base 10 of the concentration of A minus, but we just said that the concentration of HA is equal to A minus, so we can replace that with A minus, right? And I could have done it the other way around. I could have replaced the A minus with HA, but notice what you get. What you end up getting is the pH is equal to the pKa plus the log of 1. Right? So this is the log of 1. And I could drop the absolute value signs because concentrations are always positive, right? We don't have to include the absolute value at this point. But notice what happens, okay? You get, in the argument of the logarithm function, A minus over A minus. And notice that those are equal quantities. So they both end up canceling out, and you get log of 1. Now, one thing that you should be aware of is what the log of 1 is. Okay, so if I was to, and let me do this, if I was to actually draw the any kind of logarithm curve, okay, first of all, you can't take the log of a negative number, so the value that's inside this logarithm can never be less than 0. Okay, so you have to take the log of a number that's greater than 0. But your curve is essentially going to look something like this. It's going to look like this, and it's sort of going to level out as it goes off to infinity in the x direction. Okay, it's going to get flatter and flatter. And this point that it crosses the x-axis, okay, this point in the x direction it's at 1, and then in the y direction it's at 0. And that's an important thing to realize, that when you take when you have the x value equal to 1, the y value that you get out of it is 0, right? So what is log of 1? Well, log of 1 is just 0, right? And so this is one way that you can go about saying that the pH is going to be equal to the pKa. So that's one way to go about doing it. Okay, and I hope that makes sense. But there's actually another way that we can actually prove this to be the case. Let's actually go the reverse direction. Let me rewrite the equation. pH is equal to pKa plus the log base 10, where the argument is the concentration of the conjugate base divided by that of the conjugate acid. Okay, so there's my Henderson-Hasselbalch equation. Well, let's do it in the reverse direction. Let's actually figure out what the ratio of the conjugate base is to the conjugate acid. So let's say, what is the ratio at that point when the pH is equal to the pKa, right? What's that ratio? Well, again, we can say that the pH, right, is equal to the pKa. So what's the ratio of acid and base at that point? Well, if the pH is equal to the pKa, right, we can make a substitution. And we can do it either direction, but let's actually substitute pKa in right here. So what we're going to get is the pKa is equal to the pKa. Notice what I did. I just said the pH was equal to the pKa plus the log base 10, where the argument is the concentration of the conjugate base over that of the conjugate acid, right? Well, you can actually just subtract pKa from both sides, right? It's legal. If you do one thing to one side of the equation, you have to do it to the other. And what you're going to end up getting is both of these cancel out, right, to 0. So you should get 0 is going to be equal to the log base 10 of the concentration of the conjugate base divided by that of the conjugate acid. Okay, and again, those are just concentrations that can be in molarity or moles. Okay, but how do I isolate the ratio of the conjugate base to that of the conjugate acid? How do I do that? Well, what I can do is I can do an anti-logarithm, and since the base here is 10, that means I can take 10 to both sides, right? So 10 to the 0 is therefore equal to 10 to the log base 10 of the concentration of A minus over that of HA. So what happens? What's 10 to the 0 power? And really, what's anything to the 0 power? Well, that's just 1, right? That's just 1. What's 10 to the log base 10? Well, those cancel out, and so you just get the concentration of A minus over the concentration of HA, right? Well, if I want to figure out what each one is, I can just multiply both sides by HA, right? If I do one thing to one side, I have to do it to the other side, right? So over here, HA cancels, and then I get this relationship that the concentration of HA is equal to the concentration of A minus at the pH when the pH is equal to the pKa. And I hope that makes sense. And that's basically 2 ways you can go about proving that. So we've proved that the concentration of HA equals that of A minus when the pH is equal to the pKa. So I hope that makes sense. And again, where are we on the curve when that happens? Well, we're right here. This is the point where that occurs, only when the pH is equal to the pKa. So we can approximate the conjugate base concentration being that equal to that of the conjugate acid. Okay. And we'll deal more with Henderson-Hasselbalch in future videos. But just bear in mind, in the next video, we're actually going to look at the second case where we know the concentration of each species and the pKa, and then we can just go about doing a direct calculation for the pH. But keep in mind, when we know the pH, the pKa, and the total concentration of buffer, that becomes a lot more difficult, and we get a system of 2 equations and 2 unknowns. See you in the next video.